for Scala developers, for someone who are interested in Scala development or considering Scala as a future language. Today we are having as a speaker Anatolii Kmetiuk. Let me introduce Anatolii. Anatolii participating several times, actually 2 times in the ScalaUA conference. He is working for 4 years in Scala development. Currently, I am having some issues with lagging of translating to our YouTube channel. So, guys, sorry for some delays from my side. So trying to adjust. So trying to adjust to the situation. So hopefully I've managed to fix it. So just because I'm hearing myself with huge delay. So let me introduce Anatolii. Anatolii spent a lot of time working for Scala development field. So he is familiar with Finch during 1 year. So he can deliver a lot of useful information to us today, but unfortunately we are quite limited with the time. So let's try to be short and precise. So you can ask your questions on our YouTube channel chat. Also, there is some other channels, so we are checking in which way, and we'll provide you with the details. Anatolii can deliver a lot of knowledge about development of Scala backend solutions, familiar for a long time with Akka and developing API and Scala Cat libraries. So Anatolii, let me give you a word, so please start your demo.
Thank you, Victor. Hello, everyone. And first of all, I would like to thank the team of ScalaUA for presenting this great opportunity for developing this Scala community. And today, I would like to talk about creating APIs in Scala with the Finch library. So precisely, what we will be discussing today is how to create JSON-based APIs in Scala in a very nice, composable way that is actually pain-free and that is easy to work with for programmers. First of all, let me share the screen, first of all. And let me briefly make some introduction of Finch and the introduction of how we will structure this today's webinar. Finch is a tool for Scala to create JSON APIs. And first of all, JSON APIs are really important and convenient tool for web development because they allow you to have several different clients working with the same server. So the main idea of a JSON API is a web server that responds to HTTP requests with some JSON data that it has computed. So the results of the computation that the web application does are packed into JSON objects and returned to the client. So why it is important? An ordinary HTTP server usually returns an HTML text to be rendered in browser, but this limits the application of the server to browser-based applications only, to websites only. But if your server talks JSON, you are able to create both websites and any other kinds of clients that are able to work with JSON. So you may want to create a website that talks Ajax with the server. You may want to create a mobile application that performs HTTP calls and decodes the JSON responses. You may want to create some any other kind of applications that talks JSON. So this is why JSON Web APIs are popular and important. And this is why if you're interested in Scala and if you're working with backend, you may find it useful to know how to construct these web APIs in a nice and functional way. So today we will be discussing the Finch library to work with that is used to work with JSON Web APIs. So first of all, I would like to say a few words about this library. Actually, this Finch library is a thin wrapper on top of the Finagle library. And the Finagle library is a web server library that is developed by Twitter, and it is actually used to deploy servers that would listen to incoming connections and respond with some kinds of responses. So your ordinary server. And what Finch brings to this Twitter's Finagle is the ability to construct these APIs, JSON APIs, in a nice and functional way. So we will structure the overview of this Finch library in two parts today. So in the first part, we will make a little bit more in-depth discussion of the philosophy behind Finch, maybe its drawbacks and positive sides. And in the second part, we will have a look at a concrete example of how this Finch can be used in practice. So as you probably know, and I think it is widely agreed upon among practitioners, that bare theory is not really of much use in your daily work. So it is always useful to have a look at examples of how this or that tool can be used in practice. All right, so without further ado, let me cover the theory about Finch more in depth, the philosophy behind Finch more in depth. So first of all, the main thing to know about Finch, the most important thing to know about Finch, is its endpoint type. If you know what endpoints are, if you know what they are for and how they work, this means that you know probably 80 to 90% of Finch, because Finch is centered around the concept of an endpoint. So what is an endpoint? An endpoint is a description of how the server should handle some input. So usually the job of a server is to take the input from the user, the input being an HTTP request with some body, with some headers, etc. The job of the server is to take this input, this request, and then it should perform some computation, compute some useful information based on this input, and return the output back to the user. So Finch encapsulates this idea using the philosophy of a server as a function. So this is what they write in their documentation, and the endpoint is precisely this function that is supposed to handle the incoming request to compute some useful information. As you can see, this endpoint has a single abstract method of apply, which makes it a real function. So Finch endpoint is just a function that works on some input to compute some result. Now I believe it is important to understand this what this input and result are, because I have just earlier said that if you understand endpoint, then you understand most of the Finch. And to understand endpoint, you obviously need to understand what this function does, what its input and what its output types are. So the input is really nothing complex. It is a wrapper class around the request object that comes from the Twitter Finagle. So a Finch is a thin wrapper around Finagle, so input is a thin wrapper around this request that comes from Finagle. And here is how this request is defined in Finagle. So a request is an object which has the information about the incoming HTTP connection. The method, the URI, etc. The only thing to notice about this object. The only caveat is that it has the parameter, the attributes of reader and writer. And these are input and output streams, your ordinary Java input and output streams. And this actually makes this request object an impure data structure. So one catch to keep in mind about Finch is that it cannot be regarded as a pure way to write APIs. I will tell you ahead of time that this did not cause any problems to me in past. I was able to work with it as with any pure functional solution. This is because I never had to write my own endpoints from scratch, because Finch provides a pretty nice library of ready-made endpoints. But this is a key caveat to keep in mind nonetheless. To summarize, the input contains the information about the incoming HTTP request, as well as the capability to read this request and write back to the person that issued this request. Now, the result type is a little bit more complex. First of all, I would like to tell the high-level picture of what this result type does, and then we will have a look of how it actually does this. So basically, what would you expect from a well-behaved HTTP endpoint? Obviously, you would expect it to perform some computation based on your input and return you some useful information. So this is basically what the result does. And the result type represents. It represents the result of the computation made on the input that the user has issued. So if you have a look, the endpoint result type, basically the result type over here is just an alias for the endpoint result class from the Finch library. So endpoint result is the same as the result in that function signature. So to understand what this endpoint result represents, we need to understand its two attributes. You can ignore all the other attributes. The two last ones are the most important ones. So the first one is the output, and the second one is the remainder. Now the output, it contains this pretty complex signature over here. Basically, what this signature says is that this endpoint compute performs some computation only if this endpoint matches. This computation may take time, and this computation computes a value with some HTTP data associated with it. Now let us break down this information to see which part of the signature represents which aspect of what I have just said about this type. So let us start from the very middle of the signature, the type A. So the A comes from the signature of the class. So we have endpoint result of A, and A represents the type of the types that this endpoint is supposed to compute. So, for instance, if the user requests a list of all the goods that are present in a web shop, then this A will be a list of goods. If the user, for example, tries to log in, then this A may be the token that the server issues the user for authentication. Next, we have this output thing over here. The output type is defined over here in this part of the documentation. And as you can see, this output, it contains some value that we have computed, along with a bunch of HTTP-specific data. So we have the char set, the cookies, the headers, the status, so 200 or 400, for example, and stuff like that. So basically, the output here represents the HTTP information that should be written into the response that is issued back to the user. Next, we have a future over here. So the future represents the asynchronous nature of the computation. So, for instance, if your server needs to query the database to perform the computation, as most of the servers do, then this query might take time, and you do not want to block the server during this times that it takes to query the database. So this is why the output is wrapped into the future, so that the server behaves asynchronously. Finally, we have here the option type. that wraps this entire thing. And this option type represents the fact that the endpoint matches not all the requests. So for instance, if the user queries the list of all the goods that are present in a web store, you do not want to match it against an endpoint that is responsible for logging users in. So if you try to handle this input with that and with their own endpoint, then the output over here will be known. So the server says that this endpoint will not respond to your request. But if the endpoint does match against this request, then the option will be sum of the future of the output. So this was the output part that is supposed to actually compute the response to the user. Next part is the remainder thing over here. And the remainder thing over here represents the fact that the endpoint handles the input only partially. So, for instance, the endpoint may only take the information that is relevant for the computations that it is supposed to perform from the input and consume this information and then return the remainder of this input back to the user. So, for example, if the endpoint only needs the body of the request to handle this request, then this endpoint will only consume this body, and then it will return back the input without the body, because it does not need any other information to handle the request. So to summarize, the endpoint in Finch is a function that takes an input, which is the HTTP data that is sent in by the user, and then it optionally computes the output asynchronously, and with the HTTP data that is supposed to be sent back to the user. So now the main idea behind this endpoint thing in Finch is that it is supposed to be a building block that is very easy to compose one with another to build even larger endpoints. So that you apply the basic principle of engineering called abstraction, so that you are able to abstract the common logic into separate endpoints, and then construct larger endpoints from this smaller endpoint. And the main idea behind how exactly you are going to construct the larger endpoints from the smaller endpoints involves the notion of the so-called applicative functor. So if you're not familiar with the applicative functors, basically when we are saying that that something, in this case endpoint, is an applicative functor, we mean that we can take two endpoints and combine them into one endpoint that computes the result of both the first endpoint and the second endpoint. Now, this is not the theoretical definition of an applicative functor, but this is a very intuitive definition. It basically allows you to zip two endpoints. This is the intuition behind the idea of an applicative functor. All right, so I think this was enough theory. And in order to actually understand what this theory does and how it is useful in practice, we should have a look at a project that actually employs this notion of endpoints to construct the API here, the API that is supposed to be supplied to the server. So here you can see this project, and first of all, I would like to say a few words about what this project actually does, the big picture. So this is pretty much a training project that makes use only from Finch. So no database. The database is mimicked by a mutable map, and basically it tries to mimic a cryptocurrency trading website. So yes, it is. This project is actually inspired by the recent boom of cryptocurrencies. So that it may be more interesting to work on something that you can actually apply in practice. And the basic idea behind this crypto trader API is that it is a platform where users can trade cryptocurrency one with another. So basically what endpoints should be present, the endpoints that are present should allow people to register, to log in, and then they should be allowed to post announcements of what do they want to trade. So for instance, they might want to post an announcement that they want to buy some cryptocurrency for a given amount of dollars, or they might want to post an announcement that they want to sell cryptocurrency for some money. And other people might want to act upon these announcements. So this is the high-level overview of what we are trying to do, or what this project is trying to do. Now let us start the discussion of how exactly it is done with the main method over here. So first of all, let us have a look at what the main method logic actually does. And basically, the only thing that this main method does is it actually bootstraps the final server with the API that is constructed with Finch. So first of all, we define the port here, where we will listen to the incoming connections. And then we are using this HTTP server serve method to bootstrap the final server. So HTTP, it comes from the final server. It is a final server way to actually launch the server and make it working. The first argument here is the port, and the second argument over here is the API. The API part comes from Finch, and as you recall, Finch is just a thin layer on top of the final API, and this means that in order to be used with final, we must first convert it to the types that final will understand. This is done by the toServiceAs method, and what this toServiceAs method does is it takes an API over here. It is called on this API, and API is an endpoint that we have just discussed, and it turns this endpoint into a service. And a service is basically an object in Final that Final will understand and will be able to serve. Now, you do not need to understand the Final stuff to be able to use Finch, because over here, this line is pretty much the only place where we are using this Final API just to bootstrap the server, and that's it. Also, over here, we are specifying the content type of the endpoint. We are specifying that it will respond with JSON. So this was some context about how the server is started and how it uses the Finch, just so that you understand what is the place of Finch in the big picture and how we make the endpoints served to the end user. Now, the majority of our subsequent discussion will be held around this API scene over here, API endpoint over here. We will see how it is constructed with Finch, how it is easy to construct this endpoint with Finch. So let us, without further ado, let us start the discussion about how to construct this large endpoint with Finch, and more importantly, what it actually does. So this API endpoint is an endpoint that is supposed to handle all the incoming connections to the server. So whether the user wants to register, whether they want to log in, whether they want to check their balance, whether they want to place an order for purchase or sell of cryptocurrency, everything is handled by this API. Now, of course, this would require a lot of complex logic to write an endpoint that will handle any type of request. And this is a nice opportunity to see how Finch eliminates this requirement for very complex logic by allowing us to assemble this one large Uber API, Uber endpoint, from a bunch of smaller endpoints. So now let us have a look at the right-hand side of this value, how we actually compose this API endpoint. So first of all, we can see that we have a sort of an algebraic expression with the operator defined by this colon plus colon, or the coproduct operator, and the operands defined by access.all, balance.all, and order.all. Now, our application has three main aspects to it, three main logical units to it. First of all, we will need to register and login users. This is handled by the access module. Next, we will need the users to check their balance, how much money they have on their account. This is handled by the balance endpoint. Finally, we will want them to place and act upon orders, and this is handled by the order module. And now all things over here are endpoints that combine all the endpoints, all the logic that is associated with these modules. So, for instance, access.all is an endpoint that will handle all the requests regarding login, regarding signing up, regarding logging out, and regarding all the other authentication stuff. Balance.all will handle all the requests concerning the balance of the users. And finally, the order.all will handle all the requests concerning the placing and acting upon orders. Now, all these three things over here are endpoints by themselves, and they are combined into a larger endpoint API using this coproduct operator. So if you are not familiar with coproducts, you can treat them as a Boolean OR operator. They act very much like an OR operator, which means that the incoming request will first be matched by the first operand over here, the access.all. Then if it cannot be handled by this access.all, it will be again matched against the balance.all, and then it will again be matched by order.all if the balance.all was also incapable of handling it. So basically, the coproduct operator over here is a way to say that we need the API to handle both the requests to access, both the requests to all, and the requests to the order objects, both the requests to balance and to the order endpoints. So this is the way to combine these three endpoints to one larger endpoint. Now, the question is, where does this balance, access, and order come from? And actually, all these endpoints I have organized into the package called endpoints, where every of these endpoints, of these large endpoints, is organized into an individual file. So this is a pretty reasonable way to modularize such a large application, and this is a pretty reasonable and straightforward way to organize things from the engineering perspective, to keep the separate concerns in separate modules. So the catch from this discussion about the Uber API to make is that we combine large APIs from three main we combine large endpoints from three main modules of our application into even larger endpoint that is supposed to handle all the requests that are incoming to the server. Now let us have a look at how the individual modules are organized and how Finch helps us keep things modular and convenient from the engineering and composability perspectives. So first of all, let us have a look at this access module that is supposed to contain this access.all endpoint. So as I have said earlier, this access module is supposed to handle all the requests that are supposed to log in, log out, and authenticate users. So everything that is concerned with authentication goes into this module. Now, another thing to notice over here is this def called all, which we have seen in the main method over here, access.all. Here is this all. And here again, we can see this coproduct operator. So the same way as the main file, the main API is a combination of endpoints for access, for balance, and for order. The same way, the access API, the access all endpoint, is a combination of login, logout, and sign-up endpoints. So this all endpoint over here is supposed to handle either the login request or the logout request or the sign-up request. Either of these three can be handled by the all endpoint. Now let us have a look at the remainder of the content that is present in this file. So first of all, one thing that you should notice is the presence of three different endpoints here that are occurring in the all endpoint. So login endpoint is present here, logout is defined over here, and sign-up is also defined in this file. And another catch to make is that there is also this root endpoint. And this root endpoint does not appear in this def all, in this combination of these three main endpoints. And the reason why this root does not make its appearance is that it is just a built-in block that we use frequently to construct the login, logout, and sign-up endpoints. Now let us have a look in details of how it is actually done. So first of all, let us start from the simpler endpoint called root. And as you can see, it also consists of two things, this slash and the string called access, combined with the cons operator. So first of all, both these things are also endpoints. So this slash over here is an identity endpoint, and it is supposed to match everything, every input that is passed to it. Now the access endpoint is, so this access string is implicitly converted into an endpoint, and the job of this endpoint is to perform a match on a chunk of the input that is passed to this endpoint. So to summarize, this root this root constructs an endpoint that will match a path like this. So basically, we are matching against the root path, the access that is situated in the root of the server API. And the reason we are encapsulating this into a root endpoint is because we are adhering to the RESTful way of writing APIs. So this means that we have a single endpoint, URL. In this case, it is access, that is supposed to handle different requests with different HTTP methods to do different functionality. So, for instance, a POST request to this root API will cause us to log in. The delete request to this root API will cause the user to log out, and also in the sign-up method also deviates a little bit from this RESTful paradigm, because in order to sign up, we will need to perform a request to access/signup to do so. So this justifies the abstraction of the root into a separate endpoint. So keep in mind that root is an endpoint too. And now let us have a look at how it is used as a built-in block in the login, signup, and logout requests. So first of all, the login endpoint. First of all, the big picture of what this endpoint is supposed to do. First of all, it is supposed to match against to match all the requests that come to the access endpoint URL. Then it is supposed to handle only the POST requests that come to this endpoint URL. Also, it is supposed to read the JSON body of this request, because the user, when they log in, they will need to supply the login parameters, the username and password to the endpoint. So it will need to read the JSON body of the user request. And then it will need to contact the database to determine whether the user actually exists or not. Let us have a look at how this logic is realized in Finch. So first of all, what we have here is, yes, by the way, I have not mentioned about this cons and cons operator, and it is a pretty important fact that we cannot move forward without discussing. The cons operator over here actually means the sequential match of endpoints. So if the coproduct operator over here says that we can handle either login or logout or the other operand that follows this coproduct, then the cons, the sequence, says that we first need to handle the left-hand side operand, and then on the remainder of this of the input to the endpoint, we will need also to match against the excess endpoint. So in this case, in the case of root, we first match against identity against the root of the server, and then we must also match against the excess chunk of the path. So if for instance, excess is not matched by the endpoint, then the entire endpoint root will also not be matched. All right, so now we will have plenty of other examples of both the coproduct and sequence operators. So let's move forward to see how the actual endpoints are defined. So let us start from this login endpoint. First of all, the login endpoint works upon the root path. So upon the root URL. So it is supposed to handle the requests that arrive to the root URL over here. And then we modify this endpoint called root by the post function. Now, post function, it comes from the core library of Finch, and it takes an endpoint as an input, and it returns another endpoint as an output, and the resultant endpoint will be such that it will only handle the post requests. So if you look at this row root endpoint, it will be able to match any request that arrives to the given URL address. But once we pass it to the post function, the result of the post function over the root will be another endpoint that is only able to handle the post request to this address. After that, we have another sequential combination after that, we have another sequential combination of this post API, of this post request to the root endpoint and another endpoint. And this endpoint is called JSON body of login request. So JSON body is another function that that Finch provides us with as a part of its JSON is a part of its core API, and not surprisingly, what it does is it reads the JSON body of the post request and tries to parse it into a case class, into something or into any other types that we know how to parse this body to. So if you look at this login request, just to satisfy the curiosity, login request is a simple case class which contains the login string and the password string. So this is the reasonable amount of information that the user should pass to the server to log in. Now the JSON body of login request constructs an endpoint that will read the body of the post request and deserialize it to login request case class. Now, all the deserialization parsing and magic is done by the Kirke library, which is a functional library to parse JSON, and it does a pretty awesome job of knowing how to parse a JSON of JSON objects to case classes. So you can just add this import over here and use it out of the box like this. Finch has an excellent integration with this library. So even if you do not understand, even if you do not know this library, even if you are not familiar with it, there is absolutely zero learning curve that you need to go in order to use this Kirke with Finch. All right, so now the post to root, the post request to the root endpoint is combined sequentially with the JSON body endpoint to construct a larger endpoint. So the text that I have just highlighted over here is also an endpoint that is as a result of sequential combination of post of root and JSON body of login request. And basically what it says is that this endpoint will first match the post request to the root, and then it will match the JSON body against this case class. It will try to parse the JSON body of the request to this case class over here. If any of this request fails, the entire endpoint over here fails. Now, as you recall, an endpoint is supposed to compute some value as its result. Prior to this, we saw the root endpoint, and the root endpoint doesn't compute any value. It just matches the path string of the input of the user request. However, the JSON body request actually does compute some value, and it is reasonable because if we are trying to parse a JSON body of the incoming request, we want to have the parsed case class as the result. So it is only reasonable that the JSON body endpoint will be an endpoint that does evaluate, does compute some result, and this result will be a login request case class. Now what we have here is a sequential combination of an endpoint that does not compute anything post of root and an endpoint that computes login request. This results into another endpoint that computes login request. And now this is only half of the job. This is only the job that is done regarding the reading, the understanding of what the user wants from us. So the user, in this case, it wants to log in, and we have the data that they pass to us to log them in. Next step would be to actually try to log them in, to try to make use of this data that the user has passed. And here, because of the fact that endpoints are modeled around the applicative functors, we are able to use the map method on this endpoint to map the computed result, in this case login request, to something more useful. So we have this map output method over here, and it takes a function as its input. This is a large function that takes the result of the endpoint that we have just discussed, this one, and computes some other value from this input. And this large thing over here, this large endpoint, will be another endpoint with the login request mapped by this function to some other value. So essentially, we first compute the value using these two endpoints. We get the APIs that compute some value using these two endpoints combined sequentially. After that, we map this value to output. Because notice that this map function over here is not a row function map, but it is a map output function. Now to understand the difference, this output suffix of this function, let us briefly return to the definition of an endpoint to see what exactly this function, this map output function, might do and how it might be different from an ordinary map function that you know from Scala collections and from ordinary functors. So here is the endpoint result, as that the endpoint is supposed to compute at the end of the day. And the output that the endpoint is trying to compute is defined as an option of future of output of A. So this means that as you recall, the endpoint computes some value A wrapped into an output of A, and output contains the information regarding things like the cookies, the headers, the status code, and other HTTP-specific data together with this value A. So if we try to map this endpoint result or endpoint directly using an ordinary map, we will be mapping only this A to some other type B. And this means that we will not be able to specify the things like HTTP headers, cookies, status, and other HTTP specific data from within the map, because we are not computing the output of A, the output of B, but we are computing row B. And this is not always desirable. Sometimes we also want to specify the HTTP specific things from the map function. And precisely for this reason, we have this map output function. So just briefly to make it more intuitive, I can write here the signatures of map and map output with respect to endpoints. So the map would take here an endpoint of A and a function from A to B to construct an endpoint of B. However, map output will take an endpoint of A and a function from A to output of B to construct an endpoint of B. So in the second case, we are able to specify things like the status code, the headers, the cookies from the map function. And in the first case, we are not able to do so. In this particular case, we are using the map output because we want to change the status code of the result that is returned to the user if the error has occurred. And what happens in the body of this mapping function is that it takes this login request as an input. The login request is computed as a result of the APIs that we are mapping. We take this login and password. Then we are using our database, our dummy database based on that map to actually see whether the user with such password exists. And if it does exist, we return the status code of OK with this user as the payload. And the user data that is returned is effectively available to the user that is requesting this method as the output. And in case we did not find this user in the database, we return an error of incorrect login or password. So the error is defined by us over here, and it is frequently used. So I have defined it as a separate function, and it returns a bad request of exception of this string. Now both OK and bad request come from the core Finch API, core Finch library, and the difference in between them is that OK returns a response with the status code of 200, and error and bad request returns the status of 400. Now we can. Well, before we see how it works in practice, we should just briefly mention that, for example, endpoints like signup and logout are constructed the similar way to the login endpoint. We have not used any different aspect of Finch to construct these endpoints. So what we can do now is just briefly have a look at how this works in practice. I have here the SBP opened in this project, and I'm using the Revolver plugin from Spray to start the server with this restart command. So first of all, we are starting this server, and once it starts, I'll be using the Perl tests helpers to test the API. So I'll cd to this directory. And I have got here a few helper scripts that will allow me to send the HTTP request to this server and see whether it works or not. So just briefly, let us have a look at what we are going to do to test this API. We are going to use the user scripts from the user folder to first sign up the user using the sign up script. And to do so, we are sending the post request to to this URL, access/signup, and notice the payload that we will be handing to the server. The payload will be the JSON object with the first argument to the script as the login and the second argument as the password. And as we have seen earlier, Kirke allows us to work with JSON really conveniently and maps these JSON objects to case classes in a really convenient fashion. And after that, after we have signed up in this manner, we will use the login script over here that will contact the access endpoint with the JSON object with the post method to log us in. So let's try it out. User sign up. So the first argument to sign up will be the login. The second will be the password. So for instance, foo_bar. And what the server responds to us with is the JSON object with the ID of the user and the username of the user that we have just registered. So what have just happened is that the user was written to the database. Now let us confirm that everything works. So let us try to log in with some incorrect password. And we are getting an error of incorrect login or password. Now let us try to log in with the correct data. And we are getting again this data of JSON object describing the user. Now normally in a real project, you would want to return something else from the login endpoint. Precisely, you would want to return some kind of token that the user will use in future to authenticate. But this is a dummy project, so we do not have this token. We use a dummy authentication, so everybody who knows the ID of the user will be able to authenticate. Now I think we are really short of time, so I would like to briefly cover the most important aspects from the other modules that we have over here. I will not be covering in details what every of this module does. I'll just be stopping on the most important parts from this endpoint so that you have an idea of what capabilities does Finch have. So talking about balance is also nothing special besides one point. The point that I'm talking about is this authenticated user endpoint used in my balance endpoint. So as you can see, the balance module consists of only one endpoint that is used to check the current balance of the user. So the main idea is that the authenticated user is supposed to contact this endpoint with their authentication token, and the server is supposed to tell them how much money do they have on their account. And this is done via a JSON object called balance, which specifies the amount of bitcoins and dollars that a person has on their account. Now, the point is that authentication is a really frequent problem that we encounter in our APIs a lot, because a lot of methods are supposed to work only if the user is authenticated or has some role, etc. And it makes a lot of sense to encapsulate this authentication logic into a separate endpoint. What you see here is an ordinary GET request to the root, first of all, combined sequentially with the authenticated user endpoint. And this authenticated user endpoint comes from this package object of endpoints that contains some common data that is common to all the endpoints. And this authenticated user, it is also an endpoint that computes the user data, the ID and the login. So user data is also a JSON, is also a case class. And the way it does so is it works on a header of X access token. So X access token is a standard header where you ordinarily pass your access token for authentication. And header comes from the Finch core library, and header of this token is an endpoint that computes a string and this string will be the value of this token. So then after that, we map this string, in our case, the authentication string is just a user ID. So no authentication mechanism is used, but this simple demo mechanism. And but this illustrates the point. So what happens after we have the token is that we use this token to see whether it is correct or not. In our case, we see whether the user with the given ID exists in the database. And if it does exist, then we return the status code of OK. And if it does not exist, we return a status code of 400. And by the way, the status code of 400 in a sequential combination causes the entire endpoint to short circuit, and so that no further processing of this endpoint will happen. So, for instance, over here, if the endpoint authenticated user returns an output with erroneous status code of 400, we will no longer be able to map it. We will no longer map it. So this is a short circuit behavior. So as a point to make from this balance module is that we are able to encapsulate this very frequent logic of authentication into a separate package over here and reuse it along a wide range of other endpoints. Now, finally, we have the order module that is supposed to process the orders that users have. So we allow for people to place orders. So, for example, people may announce that they want to buy 5 Bitcoins for $10 or whatever other unreasonable orders they might want to place. Then we have an API to list the orders. So to return all the orders that are registered in the system, so that people can make their decision of what they want to buy or sell. Also, we have the trade endpoint over here that is used by the users. That can be used by the users to act upon orders of other people. So, for instance, if you have the order if you have an order in the system to buy 5 Bitcoins for $10, then I might act on this order by selling you this Bitcoins for $10. Finally, we have the capability to delete the order. Now, one thing to notice about this particular module is that almost all the endpoints over here, they use authentication. So we have this authenticated user with balance endpoint, which actually I do not have enough time to explain this in details, but it also is a combination of the endpoints that we already have seen, the authenticated user, the authentication endpoint, but this endpoint is further mapped to obtain some more useful data. In this case, it is the balance of the user. So as you can see, this authenticated user with balance is another frequently used endpoint, frequently used logic. So we also encapsulate it in a separate endpoint. And now one other thing that can be noticed about it, one other interesting thing that can be noticed about it, it is first of all, it is verification, it is validation. So, for instance, let us take a look at this complex order. We do not have a complex endpoint. We do not really have enough time to go in details of what this expression really does. But the point to notice about this expression is that it is still a combination of several endpoints bound together by several operators that we already know, that we have already seen. So with the documentation, you should have no problem of deciphering the meaning of this expression on your own. The only point that I wanted to make here is the validation. So Finch has the capability to apply validation to your endpoints. So for instance, if you have this authenticated user over here endpoint, we can apply the should method on this endpoint, and we can pass certain validation rule that tells us whether this endpoint, whether the data computed on this endpoint is valid or not. So, for instance, in its essence, this validation rule, well, first of all, I apologize because I said that this should is applied only on the authenticated user. It is actually applied on the endpoint that is a combination of the endpoint that actually obtains the order with the given ID from the database and the authenticated user. But for the point of discussion, this does not matter. The point is that essentially the validation rule over here is a Boolean function. A Boolean function that takes the result of the endpoint it is applied to as an input and returns true or false as an output. So this way you are able to say whether the result of the endpoint is valid or not and perform validation in this manner. And the final thing that I would like to notice is the capability of asynchronous computations. So we have previously seen the map method and the map output method, but however, let us again return to the definition of the endpoint result. We have seen how we have the map method to map A to B, how we have the map output method to use a function that maps A to output of B, but also we have the asynchronous versions of these methods that allow you to map as a result of an endpoint to an asynchronous computation. So probably it would be best to have a look at these methods defined in the documentation. So over here there are these 4 methods. So we have map that allows you to map A to B. We have map async, the synchronous version of map that allows you to compute B in a future from A. We have the map output that we have seen, and also we have the asynchronous version of this map output method. So actually, to simplify things, I have not used the asynchronous versions of the map a lot in this dummy API. However, in a real-world project, you will use these asynchronous versions a lot because almost every call to the database should be wrapped into a future. All right, so probably I'll make a little demo to demonstrate that this API actually does what I'm telling you that it does, and I'm not making things up, so that you know that it works. And then we will be wrapping up this webinar because we are talking already for an entire hour. So first of all, I'll restart the server from scratch. And we will try to place some dummy order and perform some dummy transactions in this order. So precisely to simplify the task of populating the server with some dummy data, I have here some scripts that perform this population. So for instance, these dummy users will create two users with the given username and password. So let us run it to populate the server. Dummy users. So we have the username 1 and user 2. And second, we are using the dummy orders API to place some dummy orders. And this dummy orders API, how it is defined just briefly, is as follows. So we have here the orders folder, and it has all the scripts associated with contacting the server with the purpose of buying or selling things, or selling bitcoins. So for instance, this buy here script will send this JSON object to the server, and the first argument of this to the script should be the owner, so who places the order. Then the second argument should be the amount of bitcoins they want to buy, and third argument should be the amount of dollars they want to pay to buy these bitcoins. Also, we have the authentication here, the dummy authentication with the access token header. What we will do now is we will use these dummy orders to populate the server. As you can see, the server returns us the orders and their IDs as they are written to the database. Now what we can do is list the orders, list orders. And what we get here is a JSON array with all the orders registered. And after that, we can act upon the orders. Well, first of all, we might want to check the balance of for example, the first user. So every user is given 1 Bitcoin and $1,000 by default. So, for instance, what we might want to do is for the first user to, for example, act or trade upon the order of the second user. So, in order to do that, we must pass call this trade script with the ID of the order that we want to act upon. That will be passed to the server as a JSON object, and also with the ID of the user that is buying the object that will be passed in the authentication token to the appropriate endpoint. So here we see that if you want to trade with the user of ID 1, the one that we have just obtained the balance of, we would probably want to trade to make this trade over with the user of ID 2. So as a request the order with ID 2. What you might want to do is order and then trade. Then the ID of the user that is trading is 1, and the ID that is order that we are going to consume is 2. And here we have the message that we successfully bought 2 Bitcoins or 0.2 Bitcoins for $100. Now, if we check the balance of the first user, we see that it changed from the Bitcoins changed from 1 to 0.8, and the dollars changed to 1,100. So they successfully sold their Bitcoins. Now, the second user, the balance of the second user is changed in an opposite direction. Also, if we list the orders, we see that the order that we have acted upon was consumed, so only one order was left. So this is pretty much how this API here works. And just to summarize the entire discussion, the first thing that makes Finch is so strong for constructing APIs is that it allows you to perform lots of abstraction. It gives you a lot of power of abstraction, so that pieces of logic, independent pieces of logic, can go to separate endpoints, separate modules. So we have done that. We have done that particularly with the authenticated API, the authenticated user with balance, and we reused this many times. Also, Finch does that as the part of its core APIs. So post, JSON body, all this stuff, all these endpoints are building blocks that Finch provides you with out of the box. So you might want to have a look at this Finch root of the Finch package, and you can see all these endpoints that we have seen. So we have body option, matchers on the parts of the input string, so Boolean, matchers on the cookies, the endpoints for every occasion of life. Everything is contained in this Finch core API. This is a really nice way to abstract this common logic. And another point where this Finch shines is that it gives you operators so that you can combine many endpoints into one endpoint using, well, I might even say an algebra on endpoints. I do not know whether it is appropriate to use this term for an impure data structures, because endpoints are impure, as we have discussed. But nonetheless, it feels like algebra, and in the work, it is really important. So the operators that I'm talking about is this coproduct operator, this cons operator, this sequence operator, also the operators like map, the asynchronous and output versions of the map, also some operators for validation and for rescuing, for handling errors. This is another thing where Finch shines. And the third final thing that I would like to mention where it shines is that it has a really great integration with a bunch of libraries like Kirke. So we can even have a look at their documentation. They say that they have a lot of integration with with many other libraries that are frequently used for web. So, for instance, personally, my favorite is Kirke, because Kirke allows you to convert JSON to case classes without any pain, with just one import. They are using macro magic, and for JSON APIs, it is really awesome thing to have. So I think this should at this point we can wrap up our discussion, and maybe you have any questions. Maybe I'll hand the word to our moderators. They should monitor whether you have any questions. And thank you for your attention. It was nice to talk to you.
Thank you, Anatoly. Yes, we're definitely looking forward for questions. So let me ask for questions also, and wait for a couple of seconds. Post your questions into our chat. While we are waiting for questions, so let me say a couple of words from organizing committee. Actually, if you like this project, you feel free to support us. You can donate some amount of money to help us to deliver such speeches in future, and invite many interesting personalities as Anatolii, and feel free to support this movement, not just to make this project bigger and more brighter. Okay, so waiting for your questions, guys. Please post your questions to chats. It looks like we are not having any questions for now, at least. So, Anatolii, I appreciate your participation, your great presentation. Thank you so much for delivering such interesting information to us, such bright knowledge. So, looking forward for getting some questions. So, in comments to this video that will be shared on our YouTube channel. So, hopefully, some interested person will get in contact with you after this video recording to be published, and you can discuss it later offline.
Yeah, sure.
Thank you so much. Yeah, thank you so much. It is a great pleasure you to be present. Looking forward to see you as a speaker and participant of our ScalaUA conference and some other webinars. So thank you, and bye for now. Bye.
Thank you for this opportunity. See you.
See you. Bye.